there we go. So back to what I was saying. So for each n equals 1, 2, 3, 4, if you can prove that there's some sequence, let's say this sequence is Wn, for each n, it's between two other sequence values. Let's say this one here is xn and this here is yn, right? The squeeze theorem just says that if xn approaches a and yn approaches a, and for every n, xn is or wn is between xn and yn, then wn will approach a, right? So if it's squeezed between these two sort of brown sequences, it doesn't even matter what this blue sequence is doing. As long as it's always in between, it's going to approach the same values as the two. That's squeeze theorem. Does that make sense? Cool. I can't explain it like you're 5, but I can probably explain it like you're 12. Yeah. Any other ones you wanted? Squeeze theorem. Comparison theorem is obvious. If xn is less than yn for all n, then the limit as n approaches infinity of xn is less than the limit as n approaches, I wrote n approaches infinity of yn. Right? So like if one sequence is always above another sequence, then the limit like still follows that same idea that the limit of this one is going to be bigger than the limit of this one. It's kind of just common sense, but formulated. What else do we want to talk about? Bolzano-Weierstrass isn't too bad. It's very simple to write, and it's very simple to use. And there will probably be a thing of this on the quiz, I would imagine. So Bolzano-Weierstrass is, suppose that a sequence is bounded above and increasing, so always increasing, then it is convergent. And I mean, this should sort of make, not convergent, there we go. This should kind of make sense. It's like if you have like some sequence that's like sort of doing this maybe, and then like leveling off. If you say that this is an upper bound, and if you say that it's always increasing, well then it's got to have a limit, right? Because it can't keep going forever because there's an upper bound, right? And it can't go back down, right? Because it's always increasing. So that's all Bolzano-Weierstrass is. So it converges to something up here. We don't know what it converges to, but it does converge to something.
Will
right?
we do some problems like this?
Yeah, I think so. This is the one we just did.
That's the assignment question.
Yep. Is this from your assignment at all?
No, 2.26 was the largest number.
Okay. I'm trying to think if these use Bolzano-Weierstrass. The problem is that there's not a lot of things that use Bolzano-Weierstrass that he's not testing you on. That's the unfortunate part about it. So, answer's probably not a lot of good examples. I don't know if these use it. I'm trying to think through them.
Okay, so two of us don't know what we're doing for this. Can we,
Yeah.
can you take it off?
So, I'll give you some more time, but I'll give you a start. So, So first off, what's that notation? The arrows x down arrow, or xn down arrow x and yn up arrow y. I think you covered it in one of the lectures, recent ones. No, you're close. This means that yn approaches y, and yn is increasing. So it's going up and approaching y. I think that was, yeah, I don't know. Xn down to x means that xn is decreasing and approaching x.
Oh, y could be decreasing but still be bounded above by y. This is saying that it's increasing and bounded.
Yeah, exactly. So let's see, that these sequences, so I guess the first thing to show is that those sequences are increasing, well, that xn is decreasing and yn is increasing. And the second thing to show is that they approach x, where x is, well, just say that they approach something. So that'll use Bolzano-Weierstrass, right? That they're convergent.
Can I ask a question about 1.6?
Yep.
Actually, before that, so this question over here, if you wanted to show that xn converges, I can't ask this question without having the textbook open, so I'll go back to what I have. So E1, E2, so on and so forth are finite sets, and E is defined as the cross product of all these infinite sets. Okay, so is the reasoning correct that you say that, okay, since each of the EJ are countable, they're finite, so they're countable, right?
Yep.
Or is that incorrect, actually, because countable is not the same thing as finite?
Countable is finite. Finite sets are countable. Countable could be infinite or finite.
But doesn't countable mean that you have to be able to map, there needs to be a one-to-one, there needs to be a bijection from natural numbers to this set, and if it's from natural numbers, then it means that it needs to be the natural number needs to be the domain, basically.
Yeah, so, so we're mapping from,
Can we just do D?
sorry?
Can we just do D?
Yeah.
Okay. If E1, E2, dot, dot, dot are finite sets,
Sure.
and E is defined as the cross product of E1, E2, dot, dot, dot,
Sure. Yep.
which is defined as the set bracket x1 comma x2 dot dot dot,
Yep.
where you have xj is an element of ej for all j in n.
Yep.
Then E is countable.
Then E is countable. Okay, so
The way I try to do this.
so here's where the countability piece comes in. Because you're asking about like finite versus countable. The countability piece comes in that there could be infinitely many sets.
But each individual set is finite.
Yep, but there's infinitely many of them,
Okay.
right? There's countably infinitely many of them, right? That's why there's not like a final E here. Like there's not like an EN or something at the end, because it's like an infinite series of them,
Okay.
right?
So can you use there was a proposition I think that said if A and B are countable,
Mhm.
then the cross product of A and B is also countable. At most, sorry. So if A and then the cross product of A and B is at most countable. So I kind of tried to do some induction thing where I was like, okay, if E1 cross E2 is E1 and E2 are countable at most.
Yep.
So that means across E1 and E2 are countable.
Yep.
And then now you take the first cross E1, E2 as like.
Yep. That'll work.
You can do that?
Yep. That'll work. Yep.
See, I was confused because in each element of it would be like a nested bracket cross
Yeah.
product structure.
Exactly. Yeah. So you would end up with like, you show E1 cross E2 is finite, and then you would cross that with E3, and then you would cross that with E4, right?
And that's the same as just E1 cross E2 cross E2.
Yeah.
But how is that the same?
It's isomorphic, is the long and the short of it. So, like what you would get is you would get like, for example, you might get like x1, x2,
Oh, I see.
x3, like that would be an element, right?
But then you could just remove the brackets, same thing.
Yeah. It's, like there's a different meaning to this, but this idea is isomorphic to just the cross products. Like that, right? Like just the repeated cross product. Or I guess like.
Isomorphic means
Right.
there's a bijection between two sets.
Isomorphic means that there is a isomorphism between the two sets, which is more than a bijection. It's a bijection plus, so say phi is a bijection, plus phi of, how are we doing this? Basically that phi works on the operations. So like, I'm trying to think of like how to, for your intents and purposes, yes, phi is a bijection, it's fine.
Okay.
Let's just say that. But you don't really even have to know that. Like, fundamentally, isomorphism means same shape, right? So it's like this and this are the same thing. It's just different interpretations, right?
Okay.
So another example of that could be like 2x2 matrices, right, are the same thing as 4-dimensional vectors, right? Like, they're not the same, right? Like, for example, A, B, C, D, and A, B, C, D,
Oh, yeah.
like they're not the same,
But yeah, there's an
but
isomorphism.
they're the same, right?
Yeah.
Same thing with like ax squared plus bx, or sorry, ax cubed, let's say, plus bx squared plus cx plus d, cubics. That's the same thing, right? It's just different ways to represent the same thing. So it's same shape, isomorphic.
Yeah, that relates to another question actually on the assignment where, so I tried to like say, okay, n degree polynomials,
Mhm.
you can interpret them as a z by z by z, like z cross z cross z, like this long cross product sequence
Okay.
set of the.
Can I see the question?
Yeah, sure.
There might be specific in there that I'm missing.
So you use the proof that I tried to do.
Sure. What was the original question? If you don't mind just saying.
This was the last 1.67.
That's a number of x is said to be algebraic degree n if it's a root of a polynomial. Yeah. It's minimal. Yeah. A member of x naught that is not algebraic is transcendental. So you're doing B.
And I'm doing the,
So
so I said that first we're gonna show that the set of n degree polynomials is countable.
yeah.
So I'm gonna say that, okay, there's a lot of like these
Yeah.
symbols that I have to define. So Pn of x, I'm just gonna say it's an, I'm just gonna say it's this n degree polynomial
Yeah.
where the leading coefficient is not 0.
Yeah.
And I'm gonna say it's countable. But the way I'm gonna say it's countable is I'm gonna represent any arbitrary n degree polynomial as a set of its integer coefficients.
Yeah.
Defined like this.
Cool. Yeah.
Okay, so then I go back to the reasoning where, so that right there where each of these is countable, so their cross product is countable.
Yep.
So then Pn is countable.
Yep.
So now z is the most countable implies, yeah, so that's basically what it's like up to here. And the set of all n degree polynomials is most countable. So then I'm gonna say dt is the set of algebraic numbers for some n-degree polynomial. We'll call it C.
Okay,
So I'm referring to a very specific set of.
that's fine, so for the polynomial.
Yeah, exactly. P is some polynomial in this set of n-degree polynomials.
Cool.
And then I'm saying that.
So, just to be sort of maybe a little bit more clear, when you say algebraic numbers for P, do you just mean the roots of P? Yeah. So that's probably easier to write that.
Okay.
Yeah, so it took me a minute when you were saying algebraic numbers. The symbol for that that's like commonly used,
Yeah, that would really
Is
help if I knew what.
a curly V of P,
Okay.
like a curvy sort of V. I don't know.
That's a set of roots of P.
Set of all
I
roots.
see.
Variety of
Sure. So I can literally just replace this whole thing with just V.
V. Yeah.
Okay, sure. I'll write it down. Okay.
Yeah.
So then cardinality of VP is less than or equal to n,
Mhm.
since this set is the roots of a polynomial P, and P
Yeah.
has degree n.
Yeah.
So at most it has to be less than or equal to n.
Yes. The reason I'm hesitating is because there's a theorem that says that, which is which I don't think we've proved, and it's the fundamental theorem of algebra, which says that it has at most,
And
well, it has exactly n roots in the complex numbers. It has at most n roots in the real numbers.
okay.
So you can just cite that and find that.
I can say okay.
Just say fundamental theorem of algebra. It's an important theorem, which is, and I'm an algebraist, so when I see not citing it, I'm like, yeah. Yes, it's true.
Okay, so then EP is therefore finite, so the set of roots is finite
Yep.
for any arbitrary polynomial of degree n.
Yep.
And so finally, if Pn is at the most countable n, so if the set of all n-degree polynomials is countable, and the set of roots of any arbitrary polynomial from that set is also finite, then all n-degree algebraic numbers are countable. This is basically where I don't know if this directly follows here.
I don't know if it directly follows either. I'm starting to think about it. So you have that. So it's actually, when you write Pn, that's not what you mean to say. What you're meaning to say is z of x, because Pn could be real number coefficients too, right?
Okay.
Z just means you have z coefficients of x, integer coefficients of x. I don't expect you to know that. I would have given you full marks for it either way, but
Okay.
just so that we're on the same
Sure.
page. So this is countable.
But then Pn is not countable.
Pn is not countable, no, because it's real number coefficients, right? And then you're saying that for all polynomials in z of x,
VP is countable.
v
is
of p
finite.
is countable, finite, yeah, equals n less than infinity. So that means that,
And so then I'm saying that since z of x is countable and VP for any p in z of x is finite,
yep,
this means that the set of all n-degree,
yep,
how do I say this? All n-degree algebraic. So the set of all n-degree algebraic numbers is finite.
yep,
Right.
I think that's fine. Did you ever show why, well, whether you called it Pn or z of x is countable?
Yeah, so I basically said that any arbitrary n-degree polynomial with integer coefficients
Yep.
can be mapped to a set of the cross product of all its
Sure.
integer coefficients.
Yeah,
Z
so
times
like,
Z times Z times Z. Where
Yeah.
the first Z is gonna be minus element 0.
yeah,
Is that n sure?
exactly, yeah. Yep, that works. And yeah, there's if you wanted to add in, you could do like, I guess technically, z minus 0 cross z n minus 1. It doesn't matter. I'm not gonna get hung up in that detail.
Okay.
Yeah. But yeah, that's good. Good work.
Okay, then C, I had no idea how to do it, but I don't know if we can.
Sure. Do you want me to move this on to the next slide, or are you guys still working on it? Or are you paying attention to this?
I'm paying attention to you.
Okay,
I'm working on
good.
it.
Sounds good. I'll give you guys some time more on this, and I'll keep talking.
Yeah.
The collection of transcendental numbers is uncountable. Yep. Well, that's an easy proof,
Yeah,
isn't it?
I think that is what it is. I think I put a star because I knew that this was gonna move on. Okay, yeah, so this is not waste time, but, or unless someone else.
I think it's handy
Okay.
to spend time on it. Well, here's the problem: is R is uncountable, right? R is equal to the algebraic numbers plus the transcendental numbers, right? Not plus, union, right?
Transcendental, algebraic numbers could be real, or sorry, could be rationals or irrationals,
Yep.
and then transcendental numbers are.
Defined to be the things that aren't algebraic, right?
They can't be rational. Can
They couldn't be rational because if you wanted to get any p over q, you could just do px plus q.
Sure, yeah, okay.
I got that backwards. Qx plus p, right? That's a solution to that.
Yeah, yeah, okay. So it's a set of, it's like a specialized set, it's like the subset of complement of rationals.
Complements of no,
Rationals?
it's like that. It's like, if you want to think of it like algebraic numbers, right? It's like all the set of all like that's transcendental. Transcendental is the things that aren't algebraic, just by definition.
Yeah, but that's also a subset of irrational, right? Transcendental.
The transcendentals are.
Like root 2 is an algebraic. And
Yeah, you're right. Yeah, it's a subset of.
Irrational.
Yeah, subset or not. In a subset of irrationals. And the irrationals, sorry, the rationals are in A, so it's kind of backwards to what, right? So Q is in A,
Yeah.
but AC is in QC. So it's kind of like, yeah, that's why it took me a second to work through it, but yes.
Okay. So is
so-
it enough to say QC is uncountable and AC is a subset of QC and so AC is uncountable?
Nope, because Z is a subset of R, right?
Yeah.
It is enough to say that A is countable, right? And a countable union accountable would be countable.
Right.
So, yeah, so we showed that A is countable, right? R is uncountable, we know that. So there's only two possibilities for AC, for the transcendentals, right? Either this is countable or this is uncountable. If this is countable, then you have countable union countable. So R would be countable. Like, it's not countable, so this has to be uncountable, right? That's how I would go about it. You can't ever take the union of a countable and a countable and get an uncountable.
Could you just argue that?
Yep, it's literally what I would do.
Or something we should cite to.
Just show that, if you really want to, just show that if you have some set E that's countable, that E union E is countable, right? If you can show that, that's pretty easy to show, right?
Yeah.
Just enumerate all the things in E and then enumerate all the things in, well, I guess we'll say E1 and E2, right? And just enumerate all the things in E1 and then enumerate all the things in E2. You're fine. So E1 union E2 is going to be countable. And then if you just, like, honestly,
When you say enumerate, like, how would you exactly write that?
how would I write that? I would say that you can, how do I say that formally? Here's what we'll do. Say that E1, let's say that they're infinitely countable, because both of these are infinite. Just say countable and infinite. I'll define a map from N to E1 union E2, okay, which applies, how do I do this? So f of n is going to equal 2n, let's say, sorry, I'm going to redo this a little bit. So let's say that we have a few functions. Let's say we have an f function that goes from n to e1, right? Specifically a one-to-one function.
Okay.
And then we have a g function that goes from n one-to-one onto e2.
Okay.
Then we want to make our own h function that goes to e1 union e2, right? So what you could do is you could, these exist because we're assuming e1 and e2 are countable, right? So there's got to be one-to-one functions, right? So h of n can equal a piecewise function where it's like f of 2n if n is even, and is that right? Sorry, n divided by 2. And g of n n plus, yeah, n plus 1 divided by 2 if n is odd, right? That's also a one-to-one function from n to e1 union e2.
Okay.
So e1 union e2 is countable. When I say enumerate, that's just like a
way to
shorthand.
index from.
Yeah, you can index it, right? You could that's a good way to phrase it. You could index everything in E1, and then you could index everything in E2, because you know you can index both of them countably, right? So enumerate's just the term for that. I don't know why. Because you're assigning a number to each thing in there, so you're enumerating them, right?
And now we know that A is countable because we proved that earlier, right? We proved it in actually the previous question.
Yes, exactly.
And so n degree algebraic numbers are countable is what we proved.
Yep.
And so you can generalize that to just for any n in the natural numbers,
Yep.
the n degree algebraic numbers are countable.
Yep.
And so
And there's
that's
countably many, right?
countably many, yes.
Yeah, there's countably many n's, so, yeah, exactly. How's this going?
Not good.
Not good?
I managed to show that yn is increasing,
Okay.
but I'm going to start showing that xn would have to be greater than xn minus 1 to show that it's increasing. And I'm not,
xn would need to be
less than, it would have to be
less than xn minus 1.
Yeah, and that's where I'm getting stuck.
Sure.
Is that I showed somehow that xn minus 1 is less than xn, which I'm assuming this shouldn't be possible, because that implies that the sequence is increasing.
Yeah, that's impossible. Yeah, that's unfortunately impossible. It is increasing. And it doesn't have to be strict either, right? If that helps at all. It can be less than or equal to. Do you at least see the logic as to if you were able to show that these are increasing and decreasing, how would you show that they converge to x and y?
It's a good question. I can tell you that if I could show it was bounded by something, could use the Bolzano-Weierstrass.
Exactly.
assuming that's it, I just don't know
That's exactly it.
how I chose boundaries actually, because I've been working on trying to fix my wrong result.
Yeah, I mean, yeah. You have to show it's bounded and then use Bolzano-Weierstrass. It's a pain. This is a painful one. What's the next one? Destruction of sequence converging to supremum. This one's pretty easy, I think. Yeah. I don't know if you want me to go on to the next one or if you want me, yeah, you're stuck on it.
The next one.
Sure. I think you get the idea. You do induction and then Bolzano-Weierstrass.
Yeah.
And then, yeah.
I'm just struggling to do the inductive stuff, I guess.
Yeah.
This content will be on the winter.
Yeah. I would say probably not a question this hard.
Oh.
So this is pretty hard. Yeah, so let's do this one. This is probably more appropriate for something that could be on the quiz. Suppose that E is a subset of R, it's non-bounded, sorry, non-empty bounded, and that the supremum of E is not E. Then you want to prove that there exists a strictly increasing sequence xn in E to the n that converges to supremum of E. Yeah.
I think, do we have a theorem in the lectures, and can we use it if we did, that every infinite sequence has a strictly increasing subsequence?
Yep. Every infinite sequence has a strictly increasing subsequence. Can you use that? Suppose that this is non-empty bounded.
Could we have this? Could we have that?
I feel like you did.
I think we had something similar to that. That would be the exact word.
Double check it.
Every infinite sequence within a subsequence that's increasing.
Yeah, but if we take like
What if your
negative 1
infinite
times
sequence
n,
is increasing?
there's no possible strictly increasing subsequence. Or even just not strictly increasing.
Yeah.
Could be negative 1, 2.
Well, you could just have the sequence 1,
Yeah,
right? That would contradict what you're saying.
yeah, that's just not a theorem.
No.
There was something similar.
I feel like there was something
but
similar, but I don't remember
what
it.
was.
And e to the power of natural numbers is what does that mean?
It's a sequence in E. So it's normally we would see it like R to the n, where R is real numbers. So that means like real number sequences. E to the n means sequences in E.
So what subsequence would be?
Well, he's a set, right? So it's a sequence where the things in the sequence are from the set E.
Okay.
4 is in the set.
And so it's natural numbers, that's natural numbers only they're just going to index the individual subsequences.
Yeah, so there's a reason we do that. So xn usually you'll see is in R to the n. And the reason we do that is because a sequence is actually a function from n to R, right? It takes in a natural number and it spits out a real number. So this notation is just generally used for functions from this to this. Why is that? I don't know. So usually you'll see like this is the set of all functions from A to B. Why is that? It makes a lot of sense if you think about it.
Yeah, that makes sense.
But it's kind of, if you think about like the way that exponents work, they kind of work like functions from one thing to another. But that's why we do that. It's moderately dumb, but you'll see it. Any other assignment questions?
Whenever there's a question asking you to show that there's some kind of convergence of a sequence,
Mm-hmm.
can we just, I'm not, like, sometimes it becomes really easy to just use a limit.
Yep.
But I guess we're not really supposed to do that, like we have to
Yeah,
show
you
that
should
it's
show
gonna be
it.
less than epsilon, or,
Yeah, you should show it. Exactly. You can show it using the limit definition. I'm fine
and that
with
would be sufficient for the purpose of this kind of.
Using the limit definition of like, what was it, for all, like the epsilon delta definition, right, of the limit,
Yeah, let me just find out.
which I think just boils down in this case to the definition of a sequence, a convergent sequence anyways, so just show it by definition, by the convergent definition.
So for example, there is a question, if xn converges, then xn over n also converges. So I think I literally just said, I don't remember what I tried to say, but can you just say that, well, xn converges, so you could say like as, so xn approaches a as n approaches infinity, and n approaches, and n is unbounded. Is there like a formal way to say that as n?
Well, you would just say there does not exist such an m, right? That it's bounded, but you could say that 1 over n is bounded, right? Like 1 over n approaches 0,
Yeah.
right?
Okay, so 1 over n approaches 0 as n approaches infinity, and xn approaches a as n approaches infinity.
Yep.
And so xn over n would approach 0 as n approaches infinity.
xn over n. Yeah, so, yeah, that's basically what you would do. You would need to cite a theorem on that, and I think he did it in lecture where it was like, if you have like xn, yn, if xn approaches a and yn approaches b, then xn, yn approaches ab. Yeah, you just use that here.
Yep.
Just say your sequence yn is literally 1 over n. Just apply that. That's what I would do. A lot of them are using those kind of definitions, which is fine. You have those theorems.
I'm sure you did this already, but could you go over this one again?
Yep. Yeah. Pardon me? Sure. So, how did I do that? Let's talk through it. So,
Function of algebraic numbers.
Sorry?
Algebraic numbers count.
yeah, do you know what an algebraic number is?
No.
No, that's fine. So, the algebraic numbers are the set of all solutions to a polynomial. So if you can get a certain number as a solution to a polynomial with integer coefficients, so like for example, well yeah, I should just finish what I was saying. So if you can get a number as a solution to a polynomial with integer coefficients, then it is algebraic. If you can't, then it is not algebraic, it's transcendental. So, for example, x minus 2, right? If you do x minus 2 equals 0, you get x equals 2. So 2 is a algebraic number. You could do something like 2x minus 3 equals 0. And you could solve that, and you would get x equals 3 over 2. So 3 over 2 is algebraic. So you can get, in this way, you could get any integer number like this. You get any rational number like this. So rationals and integers are all algebraic. You could also get any root you want. So you could do like x squared minus 3 equals 0. That'll give you the square root of 3, right? So square root of 3 is algebraic.
So it includes irrational numbers.
It does include irrationals, but not all of them,
Not all.
right? So like
So
pi
it's-
is not, you can never get pi out of this, right?
That's why it's a subset of it.
Exactly. So we have that, that's the idea. Now your job is to show that A is countable. So A is the set of all solutions, solutions to polynomial equations. So how do we go about this? First, sorry, Syed, right?
Yes.
Don't use this notation. This means infinitely long integer. So use like Pn but define it.
Oh,
This would mean like what you're trying to prove requires you to have like a finite n, right? So it's like a finite size of polynomial.
yeah.
Z is just all polynomials, right?
It's like that sub n. Yeah, so-
Sure, I'm fine with that.
Okay.
Yeah, sure, put it out here.
Yeah, but just like you can just define it with it.
Define something, yeah. Zn like this of x would mean a completely different thing. It would mean set of all polynomials where the integers are, the coefficients are integers between 1 and 4, or 1 and n, sorry.
Booleans are in the between one. Okay.
Yeah, so like as an example, I'm sorry, plus 2x cubed plus x to the 4, I don't know, something like that might be in x, or might be in z 2, yeah, right, because it's only 1 and 2 and 0, right, of x. Anyways, sorry, going back to this. I just saw that I misled you and I don't want to mislead you.
No, that's fine.
Back to this. So it's the A is the set of all solutions to polynomial equations. So we sort of introduced a few other notations here, and I'll just introduce them to make life easier. So let's say that Pn, let's just define that to be the set Ax, well, let's call it A0 plus A1x plus A2x squared all the way up to ANX to the n, such that AI is in Z, right? So each of these A's are integers, coefficients. So then how you would go about it is you would say that for any polynomial P in, actually, sorry, before I go to that, argue that this is countable. That's a good first step.
But you said that like the n, it goes from, a series goes from n to r. So how can something, oh no.
These are polynomials.
Oh no.
Yeah, different x. These are just like functions. Polynomials. Show that there's countably many of those. Which you can show in a few different ways, but just show that you could enumerate all of them in some way. Then show that V of P, sorry?
It's finite.
Is finite, yeah, is less than infinity. So V means the set of all solutions to the polynomial P. It's for all P in Pn. So for any polynomial, you could pick the number of solutions it has is finite. You can't have infinitely many solutions to a polynomial. This follows from the fundamental theorem of algebra. Yeah, which you can just cite that, and I'll pretend that you know, you've all proven that at some point in your life, which I don't think you have. Maybe next semester if you take complex. Sorry. Okay, so you've done that. From the fundamental theorem, you can prove that this is less than infinite. In fact, you can specifically prove that this is equal to n in the complex numbers, and that it's less than n in the real numbers, which is, I guess, what we're dealing with. Less than or equal to n. So like as an example, you can't have a quadratic that has 3 solutions. Like it's just never gonna happen, right? It has at most 2. Cubic has at most 3. So once you have that, then if you can enumerate every polynomial, and you can enumerate this n, right? Then you can enumerate each of the polynomial's roots because they're finite. So you go through each polynomial in, well, you would go through each polynomial in P1, find all of their roots. Then you would go through each polynomial in P2, find all of their roots. And then P3, find all of their roots. And then just continue that ad nauseum. That's it.
The solutions would be less than n, or equal to.
Less than or equal to n for P and Pn. So where it's an n degree polynomial. Less than or equal to. Yeah, that's the rough sketch of the proof. It's ugly, but that's the rough sketch of it. It is an ugly one. Let me see what he did, because he might have had a more elegant solution. Like, I'm an algebraist, so that's the algebraic way to do it.
We probably don't have textbook solutions.
If you don't have,
Considering all of our assignment questions come from the textbook.
if you have textbook solutions, please do not tell me about them.
Yeah,
I do not want to hear about them.
I'll say, my group does not look like that.
Let's see
I
what
probably skipped a couple steps.
Let's see what,
I don't know who that is.
Can we also take a little more?
yeah, we have, I'm just going to pull up the solution set I have for this and see how similar
Or is that
it is. Let's see. What number was that?
1.617.
1.617. It looks like you have a theorem that says that there's it looks like you have a theorem in your textbook, so this will help you. In the textbook, you have a theorem that says that z of x is countable. So the set of all polynomials, integer coefficient polynomials. Not necessarily, like it could have infinitely many terms in it. That's why I'm switching from P to Z.
Oh, so that first part, we don't have to do that.
You don't even have to do this. The theorem in your textbook is 1.42. Theorem 1.42. Just look at that in the textbook. They're countably, let's see, I don't want to read out his solution. Yep, that's basically exactly what, that's the right solution, I think. If you do this, you can take this theorem as a shortcut.
Sure.
Just save it, yep.
Isn't that what we're trying to prove? Because algebraic numbers are integer coefficient polynomials.
They're solutions to integer coefficient polynomials. So it's kind of like bringing that, I don't know why my phone's not working, there we go. It's kind of like bringing that together with the fact that there's finitely many solutions to every polynomial, right? So just bring those two together and make some argument that you could enumerate through each polynomial, yeah. Any given, since the number of, well, you don't even have to do this argument anymore either, since you already have this theorem. You can just say enumerate through each polynomial, right? P1, P2, these are all polynomials, and just list out their roots, right? List out all the roots of P1, list out all the roots of P2, off to infinity, right? You would be able to enumerate them. It would be ugly, but it was a one-to-one function.
1.6.0 would be give that.
Yeah, I don't know what it is
So,
though.
lastly,
Yeah.
if, so if integer coefficient of polynomials is countable, does that imply their solutions are also countable? No, right?
No, because they could have uncountably
Maybe so.
many, yeah. They could have uncountably many solutions. And I think the problem with that is that technically 0 is in z of x. 0 has uncountably many infinite solutions because like every number is a solution to the function 0.
What if you exclude zero?
Then it's countable.
Well, the way it was defined in the question, a 0 is included.
Okay.
0 is included.
Or 0 is excluded.
Yeah, it's excluded.
Because it's like.
Show.
Yeah, it's weird.
Polynomial of degree 0, but it forces that the nth term is non-zero.
Yep,
So 0 would have to be non-zero,
exactly.
but obviously you can't have that.
Yeah, 0 is 0. It's not non-zero.
It says that an is not 0, but what if
I didn't do it like that.
an is not
I
0?
have a feeling that all of my proofs are longer than they have to be.
What one of these is 0?
Well, that doesn't matter, but in this case, n is equal to
P n is
0,
countable because it's isomorphic to z n plus 1.
right? Because the highest degree is the 0th degree for the 0 polynomial, right?
Okay, okay.
So that would exclude 0. It doesn't matter if there's something in between that's 0. For example, in the polynomial x squared minus 2, right? There's a 0, like a1 is 0,
Yeah.
but the solutions here is square root of 2 plus minus. Both of those are fine, right? They're algebraic.
So yeah, for part B, it's a dyadic rational is defined such that x is an r is defined as a point x in R such that x is equal to n over 2 to the power n for n in z and n in natural numbers. And the set of dyadic rationals is uncountable.
Okay.
So I said that it's countable, and I basically use like I guess an isomorphism now where n over 2 to the m is mapped to Cartesian product of z and n.
Does it?
Yeah, I don't know if it's
Let's see. It might. You might be right. Z, well, the set of dyadic rationals is the set of all n over 2 to the m such that n is in z and m is in n. So, let's see.
The question says this is like uncountable, we have to say like true or false.
Okay. Yeah, they're countable. Well, they're countable. You're gonna be annoyed by this. They're countable because this is a subset of the rationals. The rationals are countable.
Oh.
You can just say that. That's pretty straightforward.
I feel like if I can swear
Right.
every single one of my proofs is like at least 10 lines longer than it has to be.
That's what I get paid for.
My prefer polynomial ones that are full page, I think.
Oh no.
Which one did you say it was? 1.6.7?
Yeah. B.
Yeah, part B.
Yeah, that's a full page.
That's a way you can do this.
The C is just that, a subset of Q.
Yeah, that's all I would do.
Okay.
Just write that. It's a subset of Q. Q is countable, so the subset has to be countable. So it can't be uncountable.
Mine's 10 pages.
Okay.
No, like 10 papers.
How did the feedback work for you guys? Like, was that,
Let's do it every.
it works? Okay. Yeah, good. I just wanted to make sure, cause like, it's a new format for me typing it, and I think it's more helpful cause I can type way faster than I can write. So I can give you more feedback but
Cut down on the, like, marking time a little bit.
cuts down on the marking time, but also like I only get so much marking time. So like in my mind, it's like either I can handwrite on your PDFs or whatever, and I'm gonna give you less feedback, or I can type it and give you more feedback, but it's not as nice because like it's not literally right on the page, right?
Yeah, that's fine.
Yeah, as long as you guys are good with that, then that's what I'll keep doing. Yeah, I think everyone did pretty well on that assignment, I would say. There was like one group who did not do very well, and everybody else was like 80s and 90s. So, good job on assignment one.
Hopefully the materials.
Hopefully.
It's so crazy, just add over.
Yeah, it's good.
Sorry?
It's just like it's irrational.
Yeah. It's irrational. Yep. Let's see.
Ben, did you take probabilities?